let's talk about the vases. There's a lot of new going on with the vases that you've been looking at.
There is.
What we talked a lot about the vases on the first podcast we did, and the incredible symmetry involved in making those vases, and the fact that they're extremely thin. You can shine a light in them and you can see through them. They're so goddamn thin, and they're made out of some of the hardest rocks on Earth. And they still say that these vases were made during those times with chisels and pounding stones and all that stuff, right?
Yeah,
even after you've come out with some of your videos and.
The hypothesis for how they were made, at least in the mainstream, has remained the same, which is, it was people rubbing on them with rocks and banging on them with flint, stuff like that. So made by hand. And again, to speed run the vases, it's like they go back to well and truly pre-dynastic times. In some cases, there's evidence of them going back to burials as far as 14,500 years ago. Right through pre-dynastic times, and then they've been found in times, basically during the Old Kingdom, up to about the 4th and 5th dynasty. Most of them, the majority of them were found beneath the step pyramid, like 40, 50,000 of them, which is a 3rd dynasty structure. Then they kind of peter out after that. Like there's a few examples of vases that come from later periods, but we identify them as coming from those periods because they have very poorly scratched hieroglyphs on them. So, we talked about that earlier. But these are incredible class and, category of artifacts, like made from all sorts of exotic types of stone. Like you said, we talked about them before. Perfect symmetry, extremely thin. Petrie found one that went down to 1/40th of an inch, which is, I think, the quote that I've got here from him. One of the other things I always like to point out is that they're often found. We talked about imitation earlier.
Painting them.
This is where you would find them, and they're ascribed to the same person because they're found in the same burial. But you have a hardstone vase here next to a hand-formed pottery vase that is painted to look like granite. And not even, this is not a turned vase, this is hand-formed.
Right.
So, a lot of people, even when you get into the details of arguing about this, the people are like, okay, they made them on a lathe, but it was just a simple lathe. Because, the idea that you're turning the stone to get these results.
Right. I'm
like, okay, so if they had lathes, why didn't they have the pottery wheel? The pottery wheel was a much simpler application of the wheel than a lathe is. But it's just a facetious sort of argument to suggest that these came from the same people. I think they're inherited and they're older. But what's happened, and there's lots of evidence, they go way back into time, lots of them discovered, they were inscribed. They were definitely reused and inherited. There's a depiction of how they were made that was found at Saqqara. This is what they used to basically say, this is how they were made. It's basically like bent sticks with weights on the side and flint tips.
This guy's got his hand in the middle of it.
Yeah, he's rubbing at it with a hand. But what they're showing you here is the vase making industry that happened after the 3rd dynasty.
Right.
It's the alabaster vases. It's just white calcite. It's a 3 on the Mohs scale. It's much softer. And we have lots and lots of examples of beautiful alabaster vase work. But it's very simple. It's not simple. It's artful. It's not precise. You don't see the same symmetry. They're off balance. They don't, they don't have the same properties as the very hard stone vases that seem to come from earlier times. So what's happened though since I talked to you last was that we've finally been able to take this analysis to a new level. Like we've finally been able to get our hands on what is a privately owned pre-dynastic rose granite vase and subject it to structured light scanning. This was the first step we've taken. And structured light scanning is a process where you're basically 3D scanning it with lasers, and you can basically create a model of the artifact down to about the accuracy of about 1,000th of an inch. So take an inch, divide it up into 1,000 pieces. A human hair is between 2 and 3 thousandths of an inch thick. A sheet of printer paper, maybe 5 or 6, something like that, thousandths thick. So where accuracy is down to less than half the width of a human hair. So it creates an extremely accurate model of the vase. Now, once you've got that model, you can start to do some interesting analysis on it. You can start to look at, okay, how precisely was this thing made? And that's exactly what we did. So this is the vase. It's actually only about yay tall. It's like 6 inches tall, maybe, little tiny thing. And that's it being scanned. And once we did that, there were a couple of professional metrologists, and these guys work in the aerospace industry. They make parts for jet engines and turbines and, the space rocket ship stuff, These are professional engineers that they're professional metrologists, and metrology being the study of the science of measurement. So in those fields, you have to you use these techniques a lot in those fields, and it's very important, right? We want to make things precisely, and this is a good example of precision enabling function. It's like turbine blade manufacture and stuff like that, like efficiency of jet engines, all that sort of stuff. These guys work for one of those companies, and this is what they do on a day-to-day basis. So they analyze the scan, and they ran it through a coordinate measurement system, and what they found was just astonishing. Like the results and looking at just how precisely this thing was made, absolutely astonishing. And in particular, it's not just the precise nature of the surfaces themselves, but it's the interrelation of one surface to another. So, making the different parts of the vase be perpendicular or parallel or perfectly aligned with other parts of it. So the way this works, it's fairly complex, but we can sort of step through it. The first thing to note is the vase itself is an ellipsoid. You can't match it to a regular geometric shape. Right? It's not a circle, it's not a sphere, it's not a cone, it's an ellipsoid. And what you want to be able to do is match geometric shapes or regular shapes to parts of the vase so that then you can do geometry on them. You can calculate center lines and center points and how perpendicular or parallel are they to other parts of the vase. So things like this. So we essentially start by creating, an XYZ three-dimensional grid, which helps us derive things like, center lines, axes, and then we can start to compare the other parts of the vase. So the way you do this in a CMM system is you match geometric shapes to parts of the vase. Now, you could do that with you could say like, all right, we're going to match a flat plane to the top of the vase, the lid, and we're going to use 5 points to do it. Mm-hmm. It's not going to be very accurate. It's not going to represent that surface very well. But if you do it with thousands and thousands of points, the more points you use of reference, the more accurately it's representing that surface. So you'll see in these slides the fact that we're using thousands and thousands of points. So in this example, there's nearly 4,000 points of reference has been used to match a flat plane to the top of the vase lip, to the top surface, and then the measurement we're doing is like how close to perfectly flat is this? It's within 3/1000ths of an inch, so it's very flat. Like that flat, the flatness of that surface is within 3/1000ths of an inch of being perfectly flat, basically. So very close, very accurate.
Around the width of a piece of hair.
Yeah, that's just the top. So then you can go further from that. Now we can look at, all right, let's look at the vase mouth. So this is that round part on the inside of the neck of the vase, if you like. And so what we're doing here is we're measuring it with a cylinder. So you can see that on the left of the vase mouth there, there's a little cylinder icon, and we're using like 10,500 points to match it, which is a lot. I mean, this actually has got some damage on the inside of the neck too, this vase. And we can match it looking at the cylindricity. So how perfectly cylindrical is that? It's within 13,000ths of an inch of being cylindrical. But now that I'll speed up a bit on this, because now that we've got that top surface, you can think of that as like an x-axis.
Right.
And if you think of a cylinder sitting in the neck of this vase, we can now, because we've matched the cylinder to the surface, we can say, okay, how perpendicular is that cylinder to the top surface that we just managed? And we call that, like the top surface is control surface A, right? So you can see like the perpendicular measurement, how perpendicular is it to control surface A, and it's within 1/1000th of an inch.
1/1000th.
Yes, so it's basically perfectly perpendicular to the top surface. Now, top surface is A, and now we've got this vase neck, this cylinder in the vase neck, and the center line of that vase neck. We can call that the axis of the vase, and we can call that control surface B. So now we can measure every other part of the vase relative to the top and the neck, and that's what we do. So we go on to measure, like, all right, you can match a sphere to the lower part of the vase body. And we did that using like nearly 80,000 points of reference, so it's really accurate. And then what you can do is with that sphere, this is worth talking about for a minute. This is the highest number we saw in the whole report. It's 17,000ths of an inch. So the center point of that sphere is basically within 17,000ths of an inch from the center line of the vase. So it's like a couple sheets of printer paper basically away from it. Now, it seems like a big number relative to the other numbers, but what this is telling you a lot more than just like how close is that center line of the sphere. What spheres are interesting, like if you took a sphere and you deformed it at all, like small on the bottom or you pushed it or whatever, it's going to shift that center point dramatically, right? Mm-hmm. So what this is telling you is not only is this 17 thousandths is no joke. Like that's extremely close. The exact center point of that sphere is really close to that center line of the vase. But it's also telling you just how regular that shape is. Because if it wasn't regular and that part of the vase that matches a sphere, if that was at all deformed, it would shift that center point all over the place. So it's telling you that it's not only is this very close to the center line, extremely close, it's almost perfectly spherical in this section. So it's a section of a sphere, that blue line, right? That's the matching of a sphere. It's very, very regular. It's regular to the point where you couldn't possibly achieve it with hand tools, by hand or by eye. Like, because you imagine you're carving on that. And again, they don't credit the Old Kingdom, or certainly not pre-dynastic times, with the use of the lathe. But even if they had a lathe, and even if you're using like a tool rest and you're trying to do this by hand, you're going to be a million miles away from this result. This is genuinely not achievable by hand.
Right.
This incredibly regular shape. It's a phenomenal achievement. And even though that's the biggest number you see in this report, this represents something that would require some of the very best machinery we have today to replicate, even in other materials like acrylic or stainless steel or aluminium. And this is in rose granite, which isn't a regular material, right? The hardness changes microscopically as it goes through the material. We get other results with same things. We're matching a cone at this point to the vase bottom. And this is the other end of the vase from the top and the center line. And we're within 5 thousandths of an inch of being perfectly perpendicular with the top. We're within 9 thousandths of an inch of being perfectly parallel with the center line, using 60,000 points of reference. Like, it's infinitesimal. It's so ridiculously well made. It's not fun, is what we're seeing with this, right?
Jesus, man.
So it gets interesting here even with the lug handles, and this gets into some of the details around how this might have been made, because you can imagine like turning this on a lathe. You can't really do the lug handles, right?
Right, exactly.
If this thing had lugs on it and you were spinning it this way, you can't, and you're cutting it as it's spinning, you can't really create the lug handles.
Yeah. They add those after in modern times.
Yeah, you'd have to. Well, these aren't added. They're
a part of one piece.
They're part of one piece.
Exactly.
Yeah, so you'd probably have to leave a bull nose and come back with a different procedure to make them.
Okay.
But we can do things like compare the match a cylinder to the lug handles, compare them to A and B, which we're doing here, and we're within 1,000ths of an inch, like 1 and 3,000ths of an inch. So incredibly accurate relative to these axes of measurement that we're taking. And then we can compare them to each other. We can create we can make one of these called reference surface F, and we can measure the other lug handle relative to it. And again, we're within 5 or 6, or I think it's 7 thousandths of an inch of being perfectly aligned. Parallel with the other lug handle. Not only that, but it's like the tops of them. Like there's actually a video of us spinning this thing on a surface and having like one of these precision tolerance gauges that measures in the thousandths of an inch, and you sort of zero it out on one lug handle and you spin it around and it just zeroes out on top of the other lug handle. Like they're perfectly the same height on the thing. And that also speaks to the flatness of the bottom, because it's turning relative to the flatness of the bottom of the vase, which we didn't measure, but that's the fact that you're zeroing out this gauge. It's in some of the videos. It's manufacturers and it's hard to explain, and machinists and people that understand these sort of measurements will understand it better, but they'll get it. But it's interesting to think, all right, so assuming you've left a bull nose, right, to create these lug handles. And you have to come back with a different tool, and you've got to carve away that area of the vase body between the lug handles. So what about that part of the vase? Because they can't be made on a lathe. It has to be made with a different process, right? And so we looked at that. We looked at the actual area of the vase between the two handles, and we found the same level of precision. And this is truly remarkable. It's 20,000 points of reference. We looked at we matched a cone to look at how close is the center line to the center line of B, like that center line of the neck of the vase. It's within 5 thousandths of an inch. This is really remarkable because in today's manufacturing processes, when you change tools or you change the process, it introduces errors. Like this is accounted for in our modern manufacturing processes, things like making turbine blades and stuff like that. We understand that tools and process changes introduces errors, and we don't see that sort of error here. We're not seeing it. So it leads you to one of two conclusions. One, whoever made this was able to handle tool and process changes better than we can, right? So they could deal with changing the process and the tool and just not have the same degree of error that we'd see. Or it wasn't made on a lathe. It was made in a single pass, which means that you're talking about 5 axes of freedom. It's a mill. So think about those CNC mills as computerized mills that can carve like a complex object with one tooltip. It's one of those two things. It has to either be
like 3D printing.
Not print. As far as we know, this is reductive.
Reductive, right?
As in we're like taking it and carving it away.
Right. Okay. Yes. Obviously. Yeah.
Yeah.
Right.
Geopolymer. The idea.
I don't mean. Yeah. Right. That doesn't make sense.
Like print, but think about like a CNC mill, like a complex 5 axes of freedom with an arm.
Yes.
That's computer guided. Like that's one of those two things that comes out of this analysis, and it's the fact that there's no perceivable lack of precision between the vase handles is amazing. So. And this is just the start of the rabbit hole kind of thing. Like it got crazy from here. This was a lot of fun because we made the STL file, like the model, available online, and sort of open sourced it. And there was a cryptographer from Denmark named Mark Kvist who runs this website called unsigned.io. Really interesting guy. I've spoken to him, and he undertook essentially a deep sort of mathematical and geometric analysis of the vase, and he found some just utterly remarkable aspects of it that I think have some extremely startling conclusions. And he kind of started by looking for, like, all right, what are there geometric patterns that we can see in this vase? So what can we see in it? And so, he kind of started and he found that it actually does encompass some of the sacred geometry that we were talking about with Randall the other day. The things like the circle of life. There's actually 2 circle of life grids that are in here, and you can see them this way. So if you look at the blue circles that measure at point D, that's a grid based on the maximum internal diameter of the vase, and you can also see that grid matches the very top of the vase with the point A. So it's a circle of life grid that matches the internal diameter, it matches the top of the vase, and then you have another circle of life grid that matches that's based on the external maximum diameter of the vase that also matches other points of it. And this is kind of where he started, and he found that it created, not only were these geometric patterns in it, but there's a bunch of these mathematically significant ratios and even algorithms and interrelationships between the shapes in the vase, to the point where you could define it with a single algorithm. And the overall point here is he's proving that this vase was designed. Like, these degrees of interrelationship between these features in the vase aren't accidental. It had to have been designed and then somehow executed in granite with just astonishing precision. So one of the base principles that he found, he's taking the object and he's reverse engineering it. Like, we're looking at it and he's trying to find out what was used, what is the philosophy, mechanism, mathematics behind this vase. And the more you dig, the more you find. So one of the fundamental principles he found in the vase is the use of the radian, or particularly the 1 radian angle. So this is a little diagram showing you what a radian is. Mm-hmm. It's a simple way to express any angle, right? You take the radius of a circle, you apply it to the circumference of a circle, the angle that it forms when you draw lines to it, on the inside is 1 radian. So if there's a 2, you could call something a 2 radian angle. Half a circle is pi radians, or 3.14, etc. radians. Right. And there are 2 pi radians inside of a circle. So it's like just an elegant way to describe any angle. Mm-hmm. And you can see the use of the 1 radian angle expressed here. So the 1 radian angle kind of defines the curvature and the angle of the top of the vase. It based on that circle of life grid center point, you can see the 1 radian angles kind of defining the placement of the handles. There's a number of different uses of the 1 radian angle. And from that, he discovered something else. He discovered that not only are there radians in this thing, but the radian is the basis for an algorithm that can be used to describe all of the curvatures used in a vase. Now, this gets a little. You don't have to understand the maths to understand the significance of this. The most widely used shape in the vase is the circle. Like sections of circles are used to describe the curves on the vase, the little tiny curves on the insides of corners and stuff like that. Now, the radius of these circles, so the size of these circles, is very tightly interrelated with each other. And it's only these radiuses. Like there's none of these, the size of these circles are accidental. They're all tightly related to each other, and they can be expressed with a single elegant equation that Mark was calling the radial traversal pattern. And that's the equation right there. But what this is telling you is that if there were circles or curves of a different radius, there's none of it. There's nothing here that doesn't fit this pattern. So it's only the circles of this size that fit this pattern. It's based on it's uses radians, but it fits this radial traversal pattern, right? So you can see it's up to there's 14 different or 12 or 14 different circle radiuses radii that he used. They're all related to each other. They're connected to each other through this algorithm.
There's that 432.
432 is here as well. And so this is. The point to take home is that this isn't accidental. You might be able to find 1 or 2 degrees of mathematical interrelationship in an object by accident, but to find 12 tightly coupled degrees of mathematical interrelationship in an object like this is not accidental. Mark actually said in the article, it'd be more likely for you to wake up one morning and have an entire new universe, like quantum universe, sprouting out of your left nostril than it would be for this to be an accident. It's not accidental. It was designed. And in order to prove this, he went ahead and said, well, you know what? Let's make a model. We're going to go into CAD. We're going to build this vase using just this algorithm, using these circles with this algorithm, make it perfect. And then I'm going to compare the vase model to the CAD model that's built using just the math. And he did that. And the median radial deviation, so the difference from the actual model of the scanned vase to the model he built using the maths, was 9 micrometers, which is 0.3 of a thousandth of an inch. Like that's the average deviation.
0.3 of a thousandth.
So like it's 3 10,000ths of an inch. Which is at that point we're talking about degrees where we don't know if it's an imperfection in the scan,
right,
or even in the vase itself. You can't tell.
Yes.
You're at the limit of resolution at this point.
What we can measure.
Yeah, so you got to also remember here that some of these circles we're talking about, they range from about 42 millimeters in size down to 1.1 millimeter at the small end. So you have arcs of circles that fit this pattern that are 1.1 millimeters in radius, which is kind of crazy, right? Very small.
What was Randall saying when you pulled this up the other day? He was like kind of freaking out.
He was. I don't think he's watched all of the videos. I'd love him to see. I want to talk. I haven't had the chance to take him through it yet, and I'll probably do that in Montana here. But
he was kind of losing his mind when he saw this because he saw something very similar with the radiuses of these circles compared to some of this plasmoid technology that he was talking about.
Yeah, and I think he would. This other stuff was interesting too. The fact that other than the radial traversal pattern, we also see pi, golden ratio. We see other sacred geometry put in here. So the image on the left shows you pi to within 0.1 of a degree. The image on the right shows us the golden ratio squared to within less than 0.1%. I'm sorry, not degree percent. Less than 0.01% accuracy with the golden ratio. There's actually the golden ratio shows up in a number of places. I've just used a couple of examples here. It also has encodes pi to within 0.1%.
Can you explain what the golden ratio is for people who might not know?
So people don't know. Golden ratio is is a fundamental principle of the world. Like it seems to be an encoded ratio that it's encoded from DNA up to the formation of galaxies. It's 1.6, et cetera. I can't actually remember exactly what it is, but it's the ratio expressed by living things. It also can be found by basic geometry. We went through it with the Randall Carlson podcast about how to define the ratio, but it can be expressed in the human body in terms of how it grows from the length of your hand down to the gap in your wrist here, and that's one part of the ratio. The other parts of it is down to here. It's the ratio is a line that is dissected where the ratio of the small to the large is exactly the same as the large to the whole, right? So it's hard to think about, but it's like take a line, the point where you dissect it, where the ratio of size is of the small piece where you've dissected it, the ratio of that to the larger piece is exactly the same as the ratio of the larger piece to the whole. So it's like
Got it.
A and B, B to A is to A plus B. Mm-hmm. That's the equation for it. Right. And it's expressed in life, right? Everything that grows, organic material, the human body, conch shells is the famous one. It's the Fibonacci sequence is attached to this. Mm-hmm. It's, you take a cross-section of a DNA molecule, you find the golden ratio. It's in the spiral helix of the DNA molecule. It's in the structure of galaxies. It seems to be a fundamental constant of the universe. And that's why I think the fact that it gets expressed in these artifacts, and in fact, this sort of geometry, even radians themselves, they're showing us, the builders of this are showing us that there's a language behind this. They're showing us their capabilities. This vase to me, represents something of almost like a time capsule. It's like something that's sent through time to us that is expressing the degree of knowledge and understanding that its creators had of the universe and of their system, even their system of mathematics. I have a slide on this later, but there was I want to finish talking about the vase because there's some interesting implications about the maths that we've been going through. I'm not doing it just for the sake of maths, but come back to that time capsule idea in a minute. But so when you think about the design of the vase and how it's been made very precisely in rose granite, and there's a mathematical design that's behind it, right? We get to a point where we're like, all right, so the precision, the complexity, the depth of interrelation between the features really rules out random chance. This artifact was 100% designed. And it's like, okay, so how could you design this? Can you design it on paper? Remember that there are circles that have a radius of 1 millimeter, basically. Mm-hmm. Imagine if you're trying to draw that at scale. I'd challenge anyone, try and draw a circle with a compass that's got a radius of 1 millimeter and see how you go. And then be able to execute that down to the thousandths of an inch. Remember, it's made extremely precisely. You might be able to draw it out on a piece of paper that's as big as the room, but then you still have to scale it down somehow. It's got to find its way to an output somehow. You've got to be able to carve this thing in granite somehow. I think the best way, and Mark proved that the best way to design this is mathematically, right? It's designed with the maths. We can express it with an equation. Once you've got that equation, you've got that mathematical design, you have to then do the same thing. You've got to get it to output somehow. So how do you take it from a design to an output and into an output of a system that is extremely accurate? Like this, just be able to make something like this in rose granite would require some of our very best precision lathes or precision mills. And you're talking about extremely sturdy and firm bearings and rods and turn screws. And it is a whole lot of capability in this, right? It's been made with astonishing precision. And the fact that we know that because of the area between the vase handles, right? It's extremely precise. Like they didn't lose positional calibration when they changed tools to make the vase handle, or it was made on a 5-axis mill in a single pass. And this is kind of where that evidence and logic all leads. And I like to use this. I like to quote directly from Mark's article where he wrote about this. And this is what he said, quoting Mark: "As far as we know, no human beings, trained animals, or naturally occurring phenomena, modern or ancient, take mathematical formulae and equations as input and produce lathe operating motions as outputs. For all the knowledge and insights we've accumulated over the ages, we know of exactly one and only one category of things capable of such behavior. The kind of thing that we refer to as a Turing machine, a device capable of taking input, holding state, performing operations on held states, according to predetermined principles, and producing output." Now, you can make Turing machines mechanically, pneumatically, electronically, hydraulically, but we call this class of device a computer, and no plausible way of representing, operating on, or manufacturing the design of this artifact exists without having access to one such. He's saying that you cannot have made this without the use of a Turing machine, aka a computer. Be able to take that design and produce the output to get the result that we see in this. It's a very interesting statement.
That's a mind. That's what we like to call a mind.
Yeah. Yeah, and it did with the mind of one of these engineers that did the original analysis of it. Remember we talked about the metrology at the start, one of these aerospace engineer guys?
Yes.
So Mark does this. And this guy's name's Nick, and he called me up. He's like, Mark puts out his article, and it took me, you got to read this article a few times and figure out the math and trying to really digest it and see what it means. And for me, this is validation. I'm like, this is magic. This is confirming some of the things that I've long suspected, and I've held this particular worldview for a while that, all right, there was technology in the past. Nick, he was amazed by the metrology. He was like, this thing's incredibly precise, scratching his head, didn't know. But it wasn't until he really sort of chewed on Mark's article. He's like, he calls me up one day and he's like, dude, I have to talk to you about this. This thing it's keeping me up at night. It's like I wake up in a sweat thinking about this vase because you could tell it had kind of shattered his worldview. It had like changed. He's like, I can't explain this or rationalize it without this type of technology. What the hell was going on in the past? And he said something to me that I was like, I put into a slide here, which I thought was really interesting. Some of the things that I've said, that I think this artifact is much more than just a simple vase, right? It's encoding sacred geometry, which is the very fabric of a universe. And I think it's telling us a tale of the creator's capabilities, their elegance, their knowledge systems, right? Even their mathematical systems, like they might have a base radian system rather than a base 10 like we use, which is an elegant mathematical system. But what Nick said to me is like, you know what this reminds me of? He said, it reminds me of the golden records that are on the Voyager space probes, right? So when these space probes went out in the 1970s, they had these golden records on them. And it wasn't like we wrote this information on there. We used mathematical principles, geometric principles. We even used the radioactive decay of I think, uranium atoms to provide a launch clock. We gave them all these clues based on different principles and maths on these vases to try and convey information about our species, about who we were, about what we knew. And we sent the goddamn things out into space. I think this vase, it seems to be something like that, but instead of going through space, it's been sent through time. It's like one of these golden records that's been sent through time to us, and and if we have the eyes to see it and the ability to decode it, there's all this information that we can glean from it, and we can learn something about the past from it. And that's what Nick was telling me. I was like, that's a fantastic analogy for it, and that's truly what it is. The deeper we look, the deeper this rabbit hole goes on this thing.